If you've ever heard engineers talk before, you may have heard them mention the term stress and strain. Of course, these are words we hear in our everyday lives, but in engineering, they have special meaning. Stress is defined as the ratio between an applied force and the area over which it is applied. Higher stress rather than force is what can cause a material to fail. For example, imagine pushing your finger into a plastic bag with a certain amount of force. The bag might stretch around your finger, but it probably won't break unless you're pushing very, very hard. If you use the same amount of force but push the tip of a pencil into the plastic, you'll probably get a hole. This is because the area of the tip of the pencil is smaller than the area of your fingertip, so the stress is higher. Strain can be thought of as the percent deformation of a material due to an applied stress. Let's go back to our plastic bag. If we cut a strip of our bag that's about 5 inches long and we pull on both ends, it gets a little longer. If it gets an inch longer, then the strain will be 1 over 5 or 20%. Stress and strain go hand in hand. When you first start stressing a material, the magnitude of the stress with respect to the strain is directly proportional, with a constant called Young's modulus.
Some materials, like rubber, have a very low Young's modulus. This means that you don't have to stress them a lot to see a lot of deformation. Other materials, like steel, have a very high Young's modulus. This means you're going to have to put a lot of force on them before you get any deformation to happen.
For the most part, there's a linear relationship between these two during the elastic region, meaning that if you stop stressing the material, it'll go back to its original shape. After you reach a certain level of stress, known as the yield stress, the material loses its elastic properties. After this, the linear relationship no longer applies, and anything can happen. When an object experiences deformation along one axis, there is usually a resultant deformation in the perpendicular direction. For example, if you ever played with these finger trap toys, you know that when you stress it axially by pulling your fingers apart, the whole thing gets skinnier, which can make your fingers stuck. You see the same thing when you throw a ball against the floor. As it squishes down in the vertical direction, it spreads out in the horizontal direction. Once again, there's a nice relationship to describe what's going on here. The opposite of the ratio between the deformation in one direction and the deformation in the perpendicular direction is known as Poisson's ratio. A material that experiences a lot of negative deformation in one direction for a small amount of deformation in the perpendicular direction has a high Poisson's ratio, and vice versa. The negative sign in this equation is because usually when a material expands in one direction, it'll contract in a perpendicular direction. Usually. Some materials, known as auxetic materials or auxetics, have a negative Poisson's ratio. What does this mean? Well, it means that if you were to pull on an auxetic material in one direction, instead of getting skinnier along the perpendicular direction, it would actually start to bulge out. Wait, how is this even possible? Let's take a look at the material at a nano level to understand. Imagine that the underlying structure of the material looks something like this bow tie lattice here. It can bend at any of these nodes. If I pull the bow tie apart, these diagonal bits will straighten, making a rectangular shape.
The average height of the bow tie is now greater,
And this increase compounds over all of these bow tie cells, leading the material to expand in the perpendicular direction. We can illustrate this on the macro level, which is a little easier to visualize. You've probably seen these expanding ball toys, known as Hoberman spheres. When you pull it in one direction, it actually expands in all directions, making for a fun little activity. There are a lot of cool applications for auxetics. Most of them involve using the materials as a mean for shock absorption. If something pushes into the material in one direction, the other axis will contract, moving more mass to the area of impact. This makes the material denser and therefore more resistant to deformation from the impact. Everything from running shoes to body armor to elbow and knee pads can take advantage of this. Another application is the field of piezoelectrics. Some materials can generate an electric charge in response to mechanical stress, which can be taken advantage of for certain kinds of sensors. Research is being done on auxetic materials and how they can enhance the efficiency of certain piezoelectric devices. Auxetics are kind of fun to think about, even though they don't match our intuition of how materials behave. So next time you sink into a soft mattress or lace up a pair of running shoes, think about how different things would be if those materials were auxetic.